Welcome. Today we shall look into some more illustrations on the microscopic mass balances. So, as we have done in our earlier lecture, we took the steady state two-dimensional momentum balance and the energy balance. Now, we are now going to deal with the species balance or the component material balance. So, here we have a steady state two-dimensional species balance in a flowing system. So, for this we can reduce the this is a steady state problem. We have steady state problem here. So, because of steady state, we know that our all the partial derivatives with respect to time will be 0, and again we are assuming the all the W components here will be a W component also, and we are taking it to be two-dimensional flow. So, we are taking the Z to be 0, this W to be 0. So, it is not appearing, and similarly here will be another term, that is dou to C A by dou Z square. Okay. So, this term is also taken to be 0 by taking that dou by dou Z is equal to 0. Okay. So, in this case we are also assuming that there is no reaction, so that there is no generation or consumption of the species A. This A is signifying the species here. So, there is no consumption and or the generation of species A. Otherwise, if there is any kind of reaction by which the species A is getting generated or consumed, then we can write that kind of a term over here. Okay. So, this will signify that there is a generation or consumption. Now, with these assumptions, now again as we have done earlier, that we are first non-dimensionalizing the equation. So, we define the non-dimensional x and y coordinate like this way, and you can see that these are also normalized. And here we are defining the u component and v component of the velocity in a non-dimensional fashion in this way. So, we are getting this non-dimensional x, y, u, v, and for the concentration again we are putting this kind of a non-dimensional equation. Now, depending on whether is C A is bound between C A naught and C A W or not, we shall be having either normalized or a normalized dimensionless concentration. So, whatever it may be, so we find that we with all these kind of transformations, what we now do, that we put all these non-dimensional numbers in the given equation, and we do the mathematical manipulations in the equation. So, this you can do very easily, and you take out all the diffusivity term outside. We are assuming that DAB is constant. This is the DAB, this is the diffusivity. So, this is the diffusivity, and this we are assuming to be constant. DAB, as we learnt earlier, that DAB signifies the diffusivity of A in another species B. Okay. So, here we are assuming that as if it has only two species, it is a binary mixture. So, with that assumption we are saying that it is a DAB. Okay. Now, if there is a multi-component mixture also, then also we can talk of diffusivity, but then we do not write like DAB, and multi-component situations are not being dealt in this particular equation, and they have a different kind of formulation for the diffusivity coefficient. Okay. So, nonetheless, whatever formulations we are deriving here, they are applicable for either binary or for multi-component systems. After this, what we find that here we have the, after rearranging the equations, we get this particular equation. This is the final equation we are obtaining. Okay, and here you can again see that we are having two dimensionless numbers. One is the Reynolds number and SC is the Schmidt number. So, SC is the Schmidt number. Okay, and this SC is equal to, from here you can see it is mu by rho DAB. Okay. So, this is the Schmidt number, and you can see that Schmidt number is a property of the fluid because this viscosity, density, the diffusivity are the property of the fluid. So, now this is the equation we are going to solve, and please understand that if we have any kind of source term, they will get added over here, and here also you will find that you will get some kind of non-dimensional numbers which will be involving the reaction rate constant along with this density and the diffusivity coefficients. Okay, so, all these things will be also coming here, and another kind of source term may come in even if it is not reacting. There could be transfer of species between two phases. Here we are talking about a single phase only. If we have suppose two phases, okay, it could be that I have a gas and a liquid, and some species is getting from the gas side to the liquid side or vice versa. In that case, this flux of the species from one phase to the other will add to a source term for this equation, and to account for that kind of source term, we have to write a flux equation for the particular species between the two phases, and this also we have covered in our earlier lecture. So, in this species balance equation may have the reaction term and the term which will accounting for some either the introduction of a species from a different phase or outgoing species from the given phase. Okay. Now, after having learnt all the non-dimensional way of the momentum equation, the energy equation and the species balance equation along with the continuity equation, we found that there are many non-dimensional numbers appearing in these equations. Now, non-dimensional numbers, there are plenty of them. So, what I am going to do now, I will be taking a few of them which we encounter very frequently. So, I will be telling about their significance and taking one by one. So, first we shall take this Reynolds number, and this Reynolds number we have seen that it is defined as the ratio of the inertia force to the viscous force. Okay, and I will not be going into the detailing and the derivation of this Reynolds number. So, I will be giving only the final term, final expression of the Reynolds number, and here you find that this is the rho v L by mu. Here rho is the density and mu is the viscosity of the particular fluid. And Reynolds number is associated with only fluids, that is gases or liquids, and not with any solids. Okay, that you must remember. So, here this is, we can also sometimes we write it like V into L and given nu. This nu is the kinematic viscosity. This is the kinematic viscosity. Okay. And you can also find this Reynolds number many times is given in terms of the volumetric flow rate, sometimes it is given in terms of the mass flow rate. So, if you want to put the Reynolds number in terms of the volumetric flow rate, it is very easy. You can see that this V is equal to Q by say A. Okay. There is volumetric flow rate divided by the area of cross section through which the fluid is flowing. So, you can put this, like for example, in a pipe of say diameter d. Okay. So, this V will be equal to Q by pi by 4 d square. Okay. And in that case, the L is taken to be the d, the diameter of the pipe. So, if you put these values over here, what you find? The Reynolds number is coming out to be q by pi by 4 d square into d divided by nu. Okay. So, and what is this? You find that this will be 4 by pi q by d nu. So, many a times you find such an expression for the Reynolds number, and sometimes it is given in terms of the mass flow rate. So, mass flow rate is, suppose G is the mass flow rate, Oh, Q is the volumetric flow rate, Then in SI unit it will be meter cube per second, and SI unit it will be kg per second. Okay. Now, you can see that this mass flow rate is nothing but the volumetric flow rate into the density. Okay. So, you can again put this, instead of Q, you can put in terms of mass flow rate, and you will get the same Reynolds number. Now, it will be R e equal to G by rho into 4 by pi by nu. And because nu equal to mu by rho, you can see it can be written as 4 G by pi into mu into d. So, sometimes you will also find Reynolds number in these terms. So, there could be many different representations of the Reynolds number in terms of velocity, in terms of volumetric flow rate, and in terms of mass flow rate. Whatever it may be, you will find that ultimately this is the ratio of the inertia force to the viscous force. And how is it important? It is important because these relative values of these two forces tell us about the nature of the flow. Nature means whether the flow is laminar or whether the flow is turbulent. Whenever the viscous effect is less, the fluid tends to have a turbulent flow. That means, whenever the viscosity is low, then the fluid is going towards a turbulent regime. And you know that the nature of the flow dictates the heat transfer and the mass transfer rates. So, the heat transfer rate and the mass transfer rate increases as the flow becomes more and more turbulent. Okay? And you know that the plug flow assumptions which we were making, in that we are making that there is a very good mixing of this. So, there in that case we were talking about that it is a plug flow because there is a fully full mixing in that particular flow. The flow rate also dictates the pressure drop. Because as we increase the flow rate, we find that the pressure drop through any particular element will also keep increasing. And many times you have found that in the fluid mechanics that the pressure drop is given as a function of the Reynolds number. Okay. So, we call sometimes all these things as thermohydraulic characteristics. Means thermo means it is the thermal characteristics, that the heat transfer rates, and hydraulic means how the pressure drop is getting affected by this flow of the particular fluid. So, as we have written here that this Reynolds number gives us the transition from the laminar to the turbulent flow, through between there will be some kind of transition flow, and the more the Reynolds number, the more the tendency towards turbulence. So, the more the Reynolds number, the more the tendency towards turbulence. Okay. So, it is not that we will always get turbulent flow. I can stay within the laminar flow, but I can still have a high Reynolds number. And you know that there is something called the critical Reynolds number, below which we assume that there is laminar flow, and above which we assume that there is a turbulent flow. And you will find that in the heat transfer and the mass transfer, you will find that various correlations proposed, and these correlations are also valid for some given range of the Reynolds number. Some correlations are valid for the laminar flow and some correlations are valid for the turbulent flow. Next we go to another number. This is the Froude number or Froude number. So many times we have we have found it in our derivation when we are deriving when we non-dimensionalized the momentum balance equation, which included the effect of the gravity. We came across this particular number, the Froude number, and this is the ratio of the inertia force to the gravity force. And as I explained you earlier, gravity force comes whenever there is a free surface, not an enclosed surface, free surface. For example, a river, a canal. So there we have a free surface, that is, it is unbound on the surface. Okay, and above that we have air. So because air has very less viscosity, so we sometimes neglect the effect of the air unless the air is passing at a very high flow rate, so that there is shear at the interface between the liquid and the gas. Okay, so whenever there is a free boundary, we talk of the Froude number or Froude number, and in this we have the effect of the gravity, because you find that in the unbound liquids only there will be wave formation. Okay, the wave formation does not come in a conduit flow. When there is a through a pipeline enclosed flow, there is no wave formation, unless otherwise you have two-phase flow. In two-phase flow only you find that there could be some kind of wavy flow, but that is having a two phases, not single phase. And two-phase flow comes when a liquid, while it is flowing, getting evaporated, or a gas as it's flowing is getting condensed. So in that case we get two-phase flow, or sometimes we also have one liquid flow and one vapor flow, and they are going together. In those cases also we have this effect of the gravity due to the difference in the densities of the two fluids. Okay. Otherwise, in an open channel flow we have the Froude number, and we have to account for this effect of the gravity. Next we come to the Prandtl number. This Prandtl number you have seen in the heat transfer analysis when we try to non-dimensionalize the energy balance equation. And here you can see that Prandtl number is given as the ratio of the momentum diffusivity and the thermal diffusivity. Please note that all these diffusivity terms, whether it's momentum diffusivity or thermal diffusivity or mass diffusivity, all of them have the same units. So you will see all of them in, if I write the dimension, it will be L square T minus 1. Okay, length and time per unit time, length square per unit time. And in case of in your SI unit, it will be say meter square per second. So all the three diffusivities will have the same unit and the same dimension. Okay. So now we write the momentum diffusivity as the same as the kinematic viscosity, that is mu by rho, and this alpha is the thermal diffusivity, that is K by rho Cp. So if you put those values over here, you will get this particular thing, that mu Cp by okay. So with this you can find that this comes to mu Cp by K. So you can see that this Prandtl number depends purely on the type of the fluid, and as the temperature changes you find that so there is a mistake over here, it will be K by rho Cp. Okay. So you can see that as the temperature or pressure changes, there will be some effect on these properties also, but generally what happens that when you take the ratio of these diffusivities, the ratio does not change much with the temperature and the pressure. So and this particular Prandtl number comes in the heat transfer analysis, and it dictates that how the momentum boundary layer changes with respect to the thermal boundary layer. And you know that boundary layer means that within which the flow is developing. So, many times you find that whenever there is a flow is developing, you find that for some time there is a boundary layer formation and then it reaches a particular constant value. So, this boundary layer may be for the momentum, maybe for the species, maybe for the energy. So, when you have this kind of situation, that I may have two types of boundary layers. So, this is the thermal boundary layer and I have the momentum boundary layer. Now, you can see that whichever is growing faster, that means it is going to reach the ultimate thickness faster. In that case, you can say that that is the other one, the slower one is going to dictate the particular phenomenon when we have a combination of the flow and the heat transfer. And when you find that this thermal diffusivity is equal to the momentum diffusivity, you find that these two boundary layers would merge. There will be only a single boundary layer. So, they tell us about the relative rate at which the heat transfer and the fluid flow are occurring. Okay. Now, next we go to the another dimensionless number which is associated with the Nusselt number. This we all with the heat transfer, that is the Nusselt number. This we also have encountered when we are non-dimensionalizing the energy balance equation, and here it is defined as the ratio of the conductive heat transfer resistance to the convective heat transfer resistance. Okay. And the resistance, you know, it is the inverse of the conductance. Okay. And this heat transfer coefficient or the K by L, this heat transfer, this 1 by H is the convective heat transfer resistance and this K by L is the conductive heat transfer resistance. Okay. 1 by K by L. Okay. So, when you plug in this, then you find that you get this is the Nusselt number. Okay. And this is the within the given fluid, that whether if you find that the fluid is very viscous, in that case you will find that generally with the increase in viscosity also you find that the thermal conductivity is coming down, even though there are independent properties. But we can say that the convective resistance becomes more and more when the viscosity increases. Okay. So, when the convective resistance increases, you will find the Nusselt number will keep decreasing, and this particular number, from this particular number you will find that many correlations are given for the Nusselt number in terms of the say Reynolds number and Prandtl number. So, from that you can find out estimate the value of this heat transfer coefficient. So, most of the correlations given in the literature to find out the heat transfer coefficient are given in terms of the Nusselt number. And you can see that if Nusselt number is equal to 1, that means both convection and conduction and convection have the same significance. And as the Nusselt number keeps rising, it goes much higher than 1. What you find that means that this convective resistance keeps coming down and conductive resistance keep going up. Okay. That means that you find that the particular, it is the conduction is the dominating heat transfer, is the controlling. That means we need not consider the convection, then we have to only focus on the conduction part. Okay. So, if it is very less than 1, then we talk of the convective heat transfer resistance more than the conduction. That means, as if the particular solid that particular fluid is highly conductive. Okay. Similar to this Nusselt number, we have a Biot number. Again, you see that Biot number is defined as the resistance by the conductive heat transfer in a solid phase and convective heat transfer within a surrounding fluid. Now, difference between Biot number and the Nusselt number is this, that Biot number has two different phases. For example, I have a solid and which is immersed in some kind of a fluid. Okay. So, now you see that whenever heat transfer is taking place, now what happens that from the boundary of the particular solid, we find that now this is the solid, and you see that in the solid what we have, that there could be in this solid there could be a thermal gradient, okay, within this solid. There could be thermal gradient. Now, if the solid is highly conductive, that means the conductive resistance within the solid is very, very less, then the whole solid may be assumed to attain a single temperature. Okay? And the resistance to the heat transfer may be taken to be only within the fluid surrounding the solid. Okay? On the other hand, if the solid has some finite conductivity effect and the fluid is going at a very high flow rate, so we may neglect the heat transfer resistance in the fluid, and we can say that the fluid is at constant temperature, whereas within the solid there will be a temperature gradient. So, these two effects within a solid and the surrounding fluid, these two effects are taken care of by the Biot number. Even though expression wise they look similar, the difference is this: in case of Nusselt number, both H and K pertain to the given fluid, whereas in case of the Biot number, H pertains to the fluid and thus K pertains to the solid which is within the particular fluid. So, this is the difference. Next, we come to Euler number. This is also related to the flow situation. In this case, we have the pressure force versus the inertial forces. This also we found in one of our derivations earlier in solution, and you can see that when we have Euler number equal to 1, we have a perfectly frictionless flow. That means both the pressure force is equal to inertial force. That means we are not, there is no contribution, because pressure loss is due to the both inertial flow as well as viscous loss. Okay. So, if the viscosity effect may be neglected, then we find the pressure loss is purely due to the inertial effect, and that is coming from the Bernoulli equation. Then we have the Grashof number. This Grashof number comes whenever we have a natural convection. Okay. That means the fluid movement is happening due to a difference in the density, and this difference in the density is caused because of a temperature gradient. Okay. What happens that when we have a temperature gradient within a liquid, the say lower part has a higher temperature and the upper part has lower temperature. So, what happens, the lower part will get less densified and then it will tend to move up into the liquid, into the top level. This is very common when you find in our kitchen, whenever we are trying to heat up some liquid, say water or milk. You find that if you put this particular thing in a transparent jar or transparent teapot, you find that you can figure out that there will be some kind of a movement of the liquid. What happens is this: the particular liquid layer which is in touch with the oven is getting heated up earlier than the fluid liquid that is at the top. So, the bottom liquid is getting less densified and it is going to the top, and from the top which have the more dense liquid, because of the lower temperature, that will tend to come down, and this way you find that there will be a convective current set within the particular liquid, and this particular effect of the buoyancy force and the viscous force is taken care of by the Grashof number, and it is given by this particular expression. Here you can see the G is coming for the gravity effect and the beta is coming due to the expansion effect of the liquid. Delta T is the driving force for the Grashof number, and then you can see that if Grashof number is very, very less than 1, then it is buoyancy effects may be neglected, and if it is much, much more than 1, then you have to take care of the viscous effect. Okay, sorry, you can neglect the viscous effect. And it is whenever you find this Nusselt number correlation for natural convection, you will find Nusselt number correlation is given in terms of the Grashof number. In case of forced convection, you will find the Nusselt number is given in terms of the Reynolds number. And we have Rayleigh number because many times we find that Grashof and Prandtl are coming together. Okay, so that way you find that we have the Rayleigh number. And we have Schmidt number, as I described you earlier. What it is? It is the viscous diffusion rate to the molecular diffusion rate, or the viscous diffusivity to the molecular diffusivity. This you can also write as nu by d. Okay, so this is the momentum diffusivity to the mass diffusivity. Okay, so this is similar to the Prandtl number, which was the momentum diffusivity to the thermal diffusivity. Okay. So it also tells us that how these two boundary layers due to the momentum and due to the species concentration would develop, and when this Schmidt number is equal to 1, that means the momentum diffusivity and the mass diffusivity are the same, so that the boundary layer thicknesses are the same. And another number which is very common, that is the Mach number. Mach number signifies what kind of flow we have and whether we have compressible flow or incompressible flow. Please understand that compressible incompressible flow is different from the compressible fluid. Okay, a compressible fluid may undergo a incompressible flow. Okay, so in this case, its Mach number is given as the ratio of the inertial to elastic force. Elastic because there is a compression and the rarefaction of the particular fluid medium. Okay, and this is also given in terms of the velocity of the sound. Okay, so this elastic force is pertaining to this compression and rarefaction of the particular fluid medium, and it is given in terms of the velocity of the particular fluid divided by the velocity of sound through that particular fluid. Okay, and Mach number, here you can see that when Mach number is less than 1, then we have the subsonic flow. When we have equal to 1, we have sonic flow, and when we have more than 1, we have supersonic flow, and when the Mach number is still more than 1, but it is still more than 5, then we call it hypersonic flow. Now, you see that significance of this Mach number is this: the type of the equations to be used for the analysis will also change. So, the equations which we use at lower Mach number will not be valid if you go for the higher Mach number. And this is, we have shown it by the movement of a rocket. Okay, this rocket also undergoes this change in the Mach number as it goes out of the Earth orbit. So, these are some of the books which you can refer to for more explanation on these topics. Thank you.